my great pleasure to introduce Dr. Dylan McNamara to today's CPEP seminar. Dylan is originally from the East Coast and did his grad school on the West Coast in San Diego, and then a short one-year postdoc at Duke University to take up a faculty position at the Department of Physics and Physical Oceanography in 2008. And then has been there ever since, has been the chair of the department for the last 6 years, and is finishing that time up now, and so is looking forward
so excited.
looking forward to returning to the army of science faculty and teaching faculty. Yeah, and he has been working on complex systems, nonlinearities, from coral reefs to sand formations to property markets. And I'm excited to learn more about how to assess sustainability and resilience of coastal communities today. So, welcome, Dylan.
All right, thank you. Thanks for having me. It's been a fun couple days so far. Already commenting a little bit about how it's a little chillier than I wanted it to be, but that's cool. I should have just come here in January, like I was saying, and just experience the full Wisconsin in January. But no, yeah, this is a great little town. I've had a good time. So I hope to kind of motivate the talk. I hope this doesn't seem too sort of pedantic, but I just wanted to motivate everyone to think a little bit about sustainability. And when you hear that word, what pops into your mind? And I know, particularly on a campus like this, where there's been some pioneering work in that umbrella of sustainability, it seems a little silly to ask that question, but still I think you'll catch my drift. Like when you hear that word sustainability, do you think about plastic straws? Does that pop into your head? Some sustainable practices, cloth grocery bags, or having a particular relationship with your use of energy and the kind of cars that you buy, the way maybe that you build your house. And this one's fun. I actually took this in the airport on the way over here. I was waiting in line for my coffee at Starbucks. When you hear sustainability, you think about how you sip your drinks. So, point of all this is to say that sustainability certainly is a buzzword now, without question. It's been greenwashed, it's been commodified, it's been misrepresented, but it is important, obviously. And I think that all this confusion about what sustainability is doesn't just hold for the lay audience. I think scientifically, I have found that depending on what particular discipline someone's from that you might be talking to, the way that they think about sustainability is different. Ecologists tend to view it a little bit differently than, say, like an environmental economist or maybe a physicist. So the goal for this talk, the big overarching goal, is to give some foundation and provide some specificity to what sustainability is, how the nonlinear dynamics community would think about sustainability, understand it, and then also the possibility that you might be able to measure it in some particular way. And so what I'm going to do is the talk has a little bit of a flavor, almost like a lecture, because I'm going to talk about some tools that I think are a little less common, particularly in the data analysis community. Tools that are a little bit less common, and I want to talk about them in such a way that everyone understands how the tools work and potentially could use them in your field, whatever it might be. And then at the end of the talk, I am going to kind of show an application of this tool set that I developed throughout the course of the talk. And that application is going to be applied to places like you see here, which is actually my hometown, Wilmington, North Carolina, during Hurricane Florence, which Till and Allie were there for. Actually, they skipped town. They weren't true. They didn't hang through it. So yeah, communities like Wilmington that suffer from natural disasters. So I'm going to use this tool set that I've developed and apply it to communities like that. And I just want to comment some wonderful colleagues who've helped me some of the work that I'll show, and then the National Science Foundation, who has reasonably generously provided me support. So I gave a talk similar to this to a lay audience, and the first thing that I did to prepare for that talk, and I gave this talk a few weeks ago, was I read a book about sustainability, the history of sustainability. I don't know if anyone's ever read this book. I recommend it. It's a really good overarching history of sustainability. So to get ourselves on sort of a common framework, I think it's good to just understand what the history of sustainability is. So I'll just hit the highlights real quick of what the book talked about. So according to the author, what they would define as the current sustainability movement started in the 70s. Like if you do like a literature search for the word sustainability in the literature, there's huge exponential growth over the last couple decades. And it really coincided with the United Nations when they got really behind sustainable development all around the world. And the book is very careful to point out that, you know, the movement of the 70s, well, of course, there are cultures, indigenous cultures that have lived sustainably for tens of thousands of years. Not all of them, right? If you've read Collapse by Jared Diamond or something, you can cherry pick out a culture here or there that maybe didn't, but for the most part, in the fabric of those communities was to live in a way with their natural environment that was sustainable. So they never really defined sustainability in any particular way. They didn't have to. We had to, Europe and during the Enlightenment, because we were the ones that started to live unsustainably. And that happened with Adam Smith and the idea of the growth economy and consumption and increasing wealth, industrialization, the invention of the steam engine, all these things started to cause serious problems, and people would look around and realize, like, there are issues. We have to think about kind of reorienting maybe the way that we interact with the natural environment. And this came to a head. This particular person, Hans Karl von Carlowitz, who was, I think he was a purveyor of salt mines, and they were running out of timber. They were using it up so fast that he realized that was a problem. So he's the person that coined the term sustainable. He wrote this document that's relatively famous on sustained yield forestry. And so that kind of kicked off, and any environmental economists are totally familiar with this world. Sustained yield forestry is what kicked off the sort of sustainability in the modern era. And then it was taken up after that by, you know, people who you might be familiar with, John Muir, over the course of the next couple centuries. And the idea became you live within limits. So this growth idea was like, okay, let's temper that. You should live within limits. And it's important to keep in mind the 3 E's, as they would call it: the environment, economics, and equity, or social issues. So all of those things have to be kind of wrapped together when you're thinking about sustainability, and you have to live within limits. So this is what you get, like the sort of Cliff Note version of what you get out of a book like this, The History of Sustainability. But for me, it still leaves me with a lot of confusion, right? Like, live within limits. Well, how do you define a limit? Like, can you define that for a particular system? Can you measure one system against another and say this one's more sustainable than this one over here? So it leaves a lot. And so for me, as someone who studies nonlinear dynamics, when I hear the word sustainability and this idea of living within limits, there's a characteristic of systems that's really important. And when I was describing this talk to a former undergrad of mine, he said, you know, you should just title it, you can't spell sustainability without stability. So it's kind of pithy, but stability is really the key here, right? Like, it's how stable is the system. So to get some insight into that, I do want to spend a couple of moments just to give you the history of where our concepts of stability have come from before I get into the weeds. And I'm going to go back to, sorry this isn't showing up the best on the screen, but this is Isaac Newton. And I'm going to go quickly back to the Principia, you know, and arguably one of the most profound contributions of man's understanding to the universe. And he really sort of set the stage for how we view the natural world and kind of attack it with mathematical tools. Famously, probably most famously, with the two-body problem. Two objects that are gravitationally attracted to each other, Sun, Earth. And in the Principia, he used his new force of gravitation and his ideas about forces and how they give rise to accelerations and yada, 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 and solved the two-body problem. And to be accurate, he actually didn't use calculus to solve it. He kind of argued for it geometrically. But that two-body problem is something that you can do in like an undergraduate physics class. You write down Lagrangian, you solve it. And the point being is that you get an exact solution. You get the position and velocity of Earth cruising around in that orbit. You get an exact solution. Okay, I'm going to contrast that with other ways to attack problems like this in a second. Now, Newton himself, when he did the two-body problem, realized there were some issues. You do the two-body problem, what would you probably try to do next? Do the three-body problem. And so the first thing he started thinking about to himself was, okay, supposedly he thought about the impact that Jupiter would have. It was really, really massive. I should probably throw Jupiter into the mix. Immediately realized he couldn't attack that problem. But he thought about it deeply. There's a fun little anecdote. He thought about it deeply, and he was pretty convinced that the impact of Jupiter on this orbit would be such that it would cause Earth to eventually fly off into outer space. And so that orbit was unstable. And he was so convinced of this that Leibniz, who you probably know was like his arch nemesis, they both think that they invented calculus and the other things the other one didn't. And so Leibniz would tease him and say that Newton's God, Newton was very religious, he would say that Newton's God is a God that if he had a watch, had constructed a watch, he'd have to take it to the watchmaker every once in a while to get it fixed. Because he thought it was absurd that a God would create an Earth going around the sun that it would eventually fly off out into infinity. So he's kind of jabbing at Newton a little bit. But that said, everyone realized that it would be important to tackle the three-body problem. So all the legends worked on it. Legendre, Lagrange, Poisson, Euler. Euler probably made the most progress, but it sat there for like 200 years about. Principia is like in the late 17th century, and it was the late 19th century that Poincaré started to attack the three-body problem with some gusto. And it's a cool history too, because the attack of the three-body problem, what prompted it in the late 1800s was the king of Norway and Sweden, I think it was, who posted it as a prize, which was common to do in those days. You get a famous problem, you post it to the community, and give somebody a cash reward for solving it. And so the cash reward for this solving the three-body problem was about a year's salary of a famous professor at the time. So he posed the problem, Poincaré attacked it, and then solved it. And we found out a few decades ago, looking through historical text, that when he originally solved it, the way he attacked it, he was wrong. He submitted a solution that was 300 pages. They started to print the journal, and his solution was actually wrong. A reviewer caught it, mailed Poincaré, and said, "Oh, this little piece of your solution doesn't really add up." And he said, "Oh, who's this person think he is?" But to his credit, he looked at it. Oh wait, they're right. So realized he'd made a mistake and worked feverishly for months to fix the mistake, and had to pay to stop the printing of the journal. And the amount of money that he had to pay, you can guess how much it cost. About a year's worth of a salary of a professor, so it was a net zero win for him. But he did figure out the issue, and in attacking what he had done incorrectly, he came up with really an entirely new way to view, for science to view how nature works. Rather than attacking it with exact solutions, he thought about it, what a mathematician would say, is a little bit more qualitatively. There's still plenty of math in there, but he thought about it more qualitatively. If you contrast their approaches, so basically what he did was he looked at, he would put a solution in that he thought was stable, and then poke at it and see what would happen to it. So rather than exact solutions where you are grinding through the equations and you're trying to get out an equation that has the solution, he thought about flows in what's called a phase space, which I'll talk about in a second. Many of you, I'm sure, are familiar. So that's the sense in which it was qualitative. Newton's approach, right, is pen and paper, analytics, works really well for linear systems, and this is still what we beat in the heads of undergraduates over and over and over again, and even in the graduate school in the physics department, you do a lot of this. This is for nonlinear systems, typically requires a computer. He invented a lot of tools, Poincaré sections and such, that he could attack this system even without a computer. But nowadays, people have to use computers to take a look at these flows in the phase space, and it's amenable to nonlinear systems. The revolution that he hit on when he took the field in this direction didn't take hold for a while. That was late 1800s. It didn't become famous again until Lorentz, the whole Lorentz chaos, in the 1960s. And so it sat dormant, partly because no one had computers, but also because there was the revolutions in quantum mechanics and relativity. So now, to put a little bit more teeth behind this, let's dig in on what this flows in the phase space business is all about. So if you have a dynamical system, you have some set of ODEs, like some flow equations basically. You have a system that has however many degrees of freedom it might have. It's something simple like a simple harmonic oscillator, position and velocity. or whatever your system might be, however many degrees of freedom it has, you have these series of evolution equations that you can view in a phase space where the axes of the space are the degrees of freedom. So if you have a simple harmonic oscillator again, its position, momentum, or velocity, say, and you think about if you put the system somewhere in that space and you give it a particular position and momentum, and you ask, what does it do? How's the flow in here? You can almost think of it like a fluid. And this is a cartoon example of a flow that you might see. If your system has dissipative processes in it, there will be a subset of that space that your system will want to go to. And that's termed an attractor. So there's flows that send you into the attractor, and there might be flows that send you away from the attractor. So in this context, stability comes in two forms. Number one, it's really important to understand what the size of the basin of attraction is. So in this cartoon example, this red region, if you start your system anywhere in there, it will flow to the attractor. And for those less familiar, right, if this is, say, a harmonic oscillator with friction, the attractor is just rest. Start it out, and then it stops eventually. So the attractor is the ending position. So you can start it in a bunch of different places, and it'll go to the ending attractor. But some systems, if you start it outside of this basin of attraction, it will go somewhere else. So that's one aspect of stability. How big is the basin of attraction? The smaller the basin of attraction, the less the stability. The other aspect of stability that I am going to dig into even more, because I'm going to show you how to quantitatively measure it, is the aspect of stability that has to do with how much the flow is converging, what its tendency is to converge. So if you analytically actually have the governing equations for your system, you can get that flow convergence very easily. Just do del dot F, and that will give you the rate of flow convergence, basically. What it really is a measure of is if you were to start, say, 4 initial conditions in the system and then let them evolve and track that area in the space and see how much that area is reducing, in this case, that is the flow convergence. That's what this is a measure of. And so, as I just said, if you start with some initial volume element in the space, however many dimensions your space is, that volume element will exponentially relax if it's converging according to del dot F. And so this is dissipation. If you have a simple system like a mass on a spring with friction, you do del dot F for that one, the answer is the friction term. So with respect to stability then, as you lose dissipation, whatever processes in your system are providing dissipation, as those are lessened, the stability goes down. More broadly, friction in a mass on a spring is one thing, but what about more broadly for systems? What are dissipative processes? They're exactly what that is telling you. They are things in your system that reduce differences or mix differences. So anything that you're thinking about, whether it's an ecological system, an economic system, any processes that you can imagine that provide dissipation are processes that give you stability in the system. And so these two aspects of stability, I'm not the first to point this out. Certainly, there's a very famous paper by Holling in the 70s, where as the world started to get their minds around with Robert May and Lorentz, nonlinear dynamics, he put an ecological sort of framework on this and defined these two aspects of stability as different kinds of resilience, he called it. He called the basin of attraction part ecological resilience, and he called this tendency for flows to converge engineering resilience. And I think because he imagined that engineers are trying to provide as much engineering resilience as possible, so if you whack your thing, it kind of fixes itself as much as it can. So but for me, it's these things that are sustainability. So now, to give a formal definition of sustainability, it's a dynamical concept that refers to the capability of a system to remain stable and within the bounds of societally acceptable parameters under some exogenous disturbance, whatever the forcing might be. So sustainability is these two things. So how would you measure that? How would you measure, say, one piece of particularly the engineering resilience part of the stability? I mean, I told you what to do if you had the actual equations, but how often do you have the actual equations for your system? So how do you measure this if you just have a time series? It's That's what I'd like to discuss now. So people have put forward some methods in the literature to get at that particular aspect of stability, this sort of flow convergence. And I'll just mention them briefly. KS entropy has been around for a while. It's analytically very elegant, but there's always that trade-off. The ones that are really analytically elegant, as soon as you put it in a real empirical setting, it kind of falls apart. Any little bit of noise, and it's just a complete mess, and all of a sudden you lose your way. So this one's mostly a theoretical construct. Permutation entropy, if anyone's ever heard of that, is a little bit more useful in empirical settings. It's a little easier to measure, but it's just not clear that it applies broadly to a lot of different kinds of systems. Critical slowing down is one that I imagine some of you have probably heard of. So critical slowing down kind of suffers from the same thing permutation entropy does. Critical slowing down applies to systems where all of the variance is when it's knocked outside of its attractor. And by definition, the attractor is a fixed point. It's a constant. And as I'll show you, and I'll kind of dig in on critical slowing down and compare it to my technique in a second, as soon as you have a system that has variance inside of it, you can't use it. It doesn't work. So I had a paper a year ago with a postdoc where we provided a new tool for measuring that aspect of stability that I talked about, temporal asymmetry and phase-space flow. So I'm going to spend some time describing how that technique works. So the system I'm going to demonstrate the technique with is the Lorentz system. Without getting into any details what the Lorentz system is, but it's the famous chaotic, Lorentz butterfly, blah, blah, blah. It's got 3 degrees of freedom. They typically are called X, Y, and Z, but in that system it's like a temperature, a velocity difference in the fluid. And this is, right, for those not familiar, it's convection between 2 plates at different temperatures. But those details don't really matter. What's cool about the Lorentz system, for those not familiar, is you look at the actual time series. So this is X, Y, and Z, the 3 different degrees of freedom through time. If you solve that system of equations on the computer for one particular setting of the parameters, you get plots that look like this, very irregular. And if I told you without showing you this is what the system looks like, and if you weren't familiar with this world, and I said, imagine you plotted this in a space, its own phase space, where the axes now are X, Y, and Z, what would it look like? You would never predict that it would look like that. So it's fascinating, it has all this structure, and there's just a whole world of cool structure in here. But I showed the time series also to illustrate, like with critical slowing down, clearly tons of variance inside the system. This is the attractor. It's not a point. It's got a whole bunch of messy stuff in here. So to illustrate my technique, I'm going to zero in on one spot on the attractor and then zoom in. And so at that spot, if you look at that red dot and think about the flow in the space around that red dot. So my technique requires you to do the following measurement. Grab the nearest neighbor to you in the phase space, K, to that point I, and measure that distance in the phase space, however many dimensions you're in. Just measure that Euclidean distance. I'm going to call that the distance at time 0. And then you march n times steps forward and measure the distance again from those same 2 points. Call that distance at time n. And then you take the ratio of those things, you sum it up all around the attractor. So you do this same game all over the place in the whole attractor. Normalized by, average it around the attractor, take the log, normalize it by however far in time you went, and we're going to call that lambda. So right, obviously what I'm doing here is I'm just representing this as an exponential increase in or decrease in those distances. And so those familiar with this kind of language, like this is a kind of a new Lyapunov exponent. So there's a couple different kinds of Lyapunov exponents. There's a global Lyapunov exponent, which is, you do not do this average. You take this out to infinity all the way around the attractor, and you see if that one exponent that you get is a positive number, which means on average for the whole entire, or out to t equals infinity for the whole attractor, that means they're diverging away from each other, which means you have a chaotic attractor, blah, blah, blah. That's the global Lyapunov exponent. There are things called local Lyapunov exponents, which is very much like what this is. Only local Lyapunov exponents, they'll take an attractor and they'll do a measure of a local Lyapunov exponent to say, well, there's some decent predictability over here, not very good predictability over here. So it's varying all around the attractor. This is like a global, local Lyapunov exponent. So you're looking at the local Lyapunov exponent, but you're averaging around the whole entire attractor, giving it this sort of global tendency. Okay, so I just mentioned that for those familiar with Lyapunov exponents. And so I'm going to call this lambda plus because we will measure, in this case, this lambda when we step L forward in time. So if you do the same thing backwards in time, you just reverse time and do the same exact calculation, I'm going to call that lambda minus. So if I do that for the Lorentz system, this is what you get. On the vertical axis is lambda. On the horizontal axis is the amount of time that you measure that separation. And the blue is the backwards in time one. The red is the forwards in time one. And then the yellow is the backwards minus forwards. So a couple interesting things here. Number one, you can see out at long times, the forward and backwards are coming to the same number. They're heading towards the global Lyapunov exponent. But they're not at the global Lyapunov exponent at these intermediate times. And in fact, if you look at this right here and say, well, this is the Lorentz system, so this is kind of a toy model. I have control of the dissipation in that system. There's a parameter that I can change and change how much dissipation there is, or how much phase-space flow convergence there is. I can do del dot F for the Lorentz system. So if you do that, and you plot, so here's the del dot F for the Lorentz system. So I've run the Lorentz system out all these different times with different amounts of friction, and so different amounts of phase-space flow convergence. And then I plotted that lambda minus minus lambda plus for each of those. And so you can see that this peak trends with the amount of phase-space flow convergence. The more convergent the space is, big negative numbers, the higher the peak. So if you just plot the peaks as a function of del dot F, it looks like that. So this is delta lambda. This is the metric that we propose in the paper as a measure of stability, or how much dissipation is in the system. So there's delta lambda on the vertical axis as a function of del dot F on the horizontal axis. So the more stable is this way, more flow convergence, and our delta lambda increases. And a couple important points. Similar with critical slowing down in every other technique, my value is not the dissipation in the system. It just trends with the dissipation, right? These numbers are not the same. That's true. But it does trend with dissipation. So this is one example system. So some follow-up questions with my technique would be, well, first of all, what if you just have a time series, right? That's how I motivated this whole thing. What if you just have a single time series? You don't have the equations sitting there for you, and you don't know what parts of the system to measure. So that's one question. What about noise? What happens if you throw noise into that picture? So we'll talk about that. And how does critical slowing down compare? So I want to get into tackling these questions. So if you just have one time series, you can do what's called phase space or attractor reconstruction. And this, if you've never seen this, it's kind of magical. The first time I saw it, it seemed sort of magical. It's actually not when you really think about it deeply, but let me tell you what it is first. So it's based on Takens theorem, which says that if you have measured just a single dynamical variable, you can embed it in an m-dimensional space, revealing the structure and determinism of the full system. The embedding process is to take your time series and construct vectors whose components are lagged values of the time series. So that's kind of a mouthful. I'll show it pictorially. So this is the Lorentz system again. So Takens theorem is basically dealing with the following thing. Imagine all you measured was x. You didn't even know that y and z existed. And you wanted to get access to that attractor. So all you measured, though, was x. So Takens theorem would say you go into the data set and you take lag values of that single variable. So you take x at some time t, you can take x at some time t lagged away from that, t plus tau, and x lagged at some other t plus 2 tau. I always think about this like a fork. It's like you're sampling your time series with a fork. And So it's got 3 prongs and they're stretched out by tau, and you're going through your time series and just sampling it like that. So you grab that one poke of the fork in your time series, and that puts you in this space there. That's the vector. And then you do it again. You go down and poke the time series again, and you do it again. And if you do that all the way through the time series, this is what you would get for the Lorentz case. And what Takens proved was that topologically, you have found the same attractor. All of the properties of the attractor are in your reconstructed version. And the reason, I mean, it seems pretty cool, right? You get the attractor even though you never saw Y and Z. Part of the reason you do, I mean, Takens' theorem is a mess to try to understand, but he doesn't say this, but I think like the essence of it is that, you know, your equations are all coupled together. So when you're looking at dx dt, it's got y and z in there. And dy dt has x, y, z in there. So as soon as you're seeing x, if you just think about x as like a finite difference thing, as soon as you have x, you also have y and z information, right? So it's not that surprising that you can do this. It's still pretty cool. One question you might ask yourself is, when you do this, like, yeah, here we can look at them visually and say, hey, topologically, look, 2 holes, they're the same thing. But how do you know, in the real world, you don't have the real attractor. So how do you know when you do this if you have something that's useful? So how do you know when you have an attractor? So the way that people attack that is to utilize the fact that determinism really dictates what's going on in this space. Right? And so what determinism is if you have a condition of a particular value of your 3 degrees of freedom, determinism means you know what's going to happen in the future. So if you revisit this part of the space and get there again, you better go in the same direction. If you go crisscross, that's a problem. And one thing I should say, I forgot to mention, I'm sure some of you are thinking about, how do you know what tau to use? How do you know how many dimensions to embed your reconstructed attractor if you don't have the equations? So there's a whole, cottage industry for picking tau and the embedding dimension. What's typically done for the embedding dimension is you use a test called the false near neighbors test. I'll just mention it so you can look it up in the literature if you want without explaining it in much detail. But that never gives you a perfect answer, so typically what you do is explore a couple embedding dimensions around what you think is the answer. That's what people typically do. And the taus, you basically want to get in your time series. You want to jump far enough away with your lagged value that there's no more information there relative to the one that you were at. You can think of it like autocorrelation. You want to get far enough away that it's not autocorrelated anymore. What people most commonly use is the average mutual information. They see that go to a minimum in lag and the actual time series. So anyway, all that to say, there are techniques out there for picking tau and the embedding dimension. So how do you know when you have an attractor? You go to a spot and you say, all right, let's make a prediction of what's going to happen in the future for that yellow point. And the way that we'll make that prediction is let's look at the closest neighbor trajectories, see what they do, and then predict that's what the yellow point's going to do. So that'll work pretty well in this case. If you increase the neighborhood size that you go and grab neighbor trajectories, then your prediction won't be as good. So what's commonly done is to generate plots like this. Your prediction accuracy, how well you did predicting, measured in this case by a correlation coefficient between the actual and the predicted value. So the correlation coefficient as a function of how large the neighborhood is that you used to generate your prediction. So here there's some parameter theta that I can use in this making these predictions to control how far away I look to grab trajectories to make predictions. And so if in a perfect Lorentz case, you see very clearly you do the best with a really localized neighborhood. And that's what determinism is, right? That's what's so cool about phase space. It is determinism. To the extent that there are rules that tell you where to go when you're in a particular place in the space, that's what determinism is. And you can see the impact of adding noise. If I just sprinkle noise in the Lorentz system, it just reduces this. And if you keep adding noise and it's just a completely noisy system, it'll flatten it completely out. So when you reconstruct an attractor, you want to make a plot like this and see if you get some indication that localized neighborhoods give you the best predictions. So my technique, when you do it on a reconstructed Lorentz, there's that example. So this is my delta lambda for stability as a function of del dot f. This is what we saw before. This is when I just use x, reconstruct the Lorentz attractor, and then measure my stability technique. Still see an indication that it trends with stability. Now here's where we put in multiplicative noise to Lorentz System and reconstruct it. So it's multiplicative noise, it's not just added on noise. And I expanded this over a larger del.f range, and you can see that on my metric, delta lambda still trends with stability. And here's where I'm comparing to critical slowing down, the typical metrics, lag 1 autoregression coefficient and the coefficient of variation. You can see that coefficient of variation is effectively useless. This does seem to trend, maybe, but then if you just go to one other, the second most commonly used toy chaotic system, the Rossler system with noise, you get that. So mine still trends with the dissipation because I can analytically adjust the dissipation in these toy cases. Mine still tracks. This one flips the other way. So the critical slowing down is not useful here at all. At all. And again, it's because the variance and the variability is inside the system. So it's not that simple relaxation to a fixed point world that those folks are in. And then in the paper, one application that we used, I'll jump to another application that I talked about, natural disasters, but before I do that, I'll show you this application that was in the paper that was kind of cool, that made me feel like there is something to this. We took the S&P 500 data in 1985, 1987, and 1989 and analyzed what our metrics said for delta lambda, comparing those 3 years. So when we did our reconstruction of the S&P 500 data, it seemed like an embedding dimension in here was the right answer using the false near neighbor test. So we explored this over those 3 embedding dimensions just to be complete. And what we saw was our stability metric, delta lambda, a lot lower in 1987. This is dating me now, but I remember Black Monday in 1987. That was a huge stock market crash. So what our metric is saying was that the stock market was much more stable in 85 and 89 than it was in 87. A lot more dissipated processes in the market in those years than in the year that ended up having a huge stock market crash. And you don't, by the way, see this just by looking at variance if you want to do some critical slowing down thing. Okay, so now to an application that's a little bit more in line with what we think about here, environmental issues. So I'm going to motivate this the way I actually was motivated to attack this problem, or when I was motivated to jump into this, was by reading a bunch of news stories like this. You see, these I picked off NPR from a few years back. And here's a quote from one of these stories. And I'll just read it to kind of bring the point home. For many families, the nightmare of a catastrophic flood is only just getting started when the waters recede. But that nightmare, one that has become increasingly common across the United States, may be worse depending on who you are. So that's interesting, right? So the disaster is worse depending on who you are. This is an issue that is explored, natural disasters and how they impact folks certainly is something that is attacked on huge, large global scales with respect to climate change. But if you think about it, often attacked in the following way. The forcing is worse over here, and so those are the people who are going to be most affected by it. The Maldives are really low-lying, sea levels rising, that's why they're going to suffer. So that is attributing the impacts to the forcing. Whereas what I'm pointing out here is something about the internal system dynamics are different, not that the forcing is different. And nowhere was this more evident to me than during Hurricane Florence. Till and Allie may remember this, the way that neighborhoods were hit, the amount of damage that they suffered was different from one community to the next. And you come back weeks and months later, the blue tarps are left on roofs in some communities, but in other communities, the blue tarps are off the roofs very quickly. The insurance process is a pain in the butt for a lot of people, but I was able to take off work and do the insurance process and go and do those things, and there's plenty of communities that didn't have that luxury. So the way that Florence impacted our region was different from neighborhood to neighborhood. And it's not, and those differences, I'll just say again, it's not because there's more water in one neighborhood relative to the next. Everything else being equal from a forcing standpoint, the internal system dynamics are different in one neighborhood relative to another. So the question I asked myself then was, can I measure the relative stability of these different communities that are subject to hazards? So what I did was, got my colleagues, my econ colleagues, got me a wonderful property value data set. I had property value in counties in this whole region that you see here. But then I grabbed property values just in the red counties that you see. Those are all counties that had a FEMA payout of some kind, whether it was for a tornado damage, flood damage, or hurricane damage. Over the last 25 years, I think it is. I'll show the time series in a second. So I grabbed those property values out. And then, of course, you can't just work with those raw property value time series. You got to do a whole world of, in econ they call it a hedonic analysis. We would call it like a regression, basically. You got to regress out how many bedrooms the houses were. You take all that property value info, so regress out how many bedrooms, was there a pool, what was the square footage, in a nice neighborhood. You get all those things out of it, so you have just a raw value time series. And then, not only that, we did, and I'll show you examples, some time series. We did the price returns, so the differences from one time moment to the next. So we have that data from 2000 to 2016, and this is what the time series looks like. The other thing we had to do was take out large trends in the market, like the boom and bust of 2008. So we would take like a consumer home price index and regress out that piece too. So we get just these property value time series, these price return time series. And without getting into too much detail on this part, because it would take a minute, but I'll just say that I did an attractor reconstruction. And what you might be asking yourself is, it's not just one time series, right? I have all these time series. And they're relatively short. So what you can do in a case like that is you can do each of those, reconstruct them and put them all in the same space. So it's almost like building the Lorentz attractor with a bunch of chopped up spaghetti noodles. So it's like you put one noodle in, and then you put the other noodle in, and then you put the other noodle in, and you put the other noodle in. So you're getting a picture of the attractor, but it's not a long, continuous noodle. It's a bunch of chopped up noodles. So I did the attractor reconstruction. And then the first thing you do when you do an attractor reconstruction, like I mentioned, is you want to do the test to see if you have a viable attractor. So here's that same plot I showed before. Correlation coefficient and your prediction accuracy as a function of the local neighborhood you use to make predictions. Basically exploring determinism in the attractor that's reconstructed. There's Lorentz plus noise, and here's my home price index returns, the black curve. So you can see that there is some indication that there's determinism in the system. There's some flow. The flow in the phase space is a function of where you are, because you do best predicting in relatively local neighborhoods. So it's some indication that you have a viable attractor. So what I actually did was, rather than do a single attractor for this all these red ones, I split them into two, based on how wealthy the neighborhoods were. So I did one attractor reconstruction for all the wealthy half, and I did another attractor reconstruction for the less wealthy half. We got census data to see how what the incomes were in all those counties. And so then I measure the stability in the wealthy community relative to the poor community subject to these natural disasters. And so this whole entire talk was just so I could show you this one plot. And here it is. So this is my delta lambda stability as a function. So I had to do it for multiple embedding dimensions for similar reasons that I showed before. And this is for the wealthy regions. This is for the relatively less wealthy or poor regions. And yeah, I didn't split it evenly, you might be noticing. So this is the percentage of people below the poverty threshold, less than 10% of the population here. This is for all the property value data where it's larger than 15%. So we found the middle line, threw the middle ones away, and then kind of cut them in half. That's the reason for that slice right there. So what this is suggesting is jiving at least with my anecdotal awareness of what happened there in Florence, right? These communities have processes in them that are providing dissipation, conferring stability to them in the face of natural disasters, more so than those over there. Okay, that is it. So I do want to mention a few caveats before I conclude, as they relate to what I just showed you. These are important. So property value is but one measure of a community. there are long timescale social dynamics that play a large role in conferring stability. I don't mean to suggest that some neighborhoods are unstable. You know, there are social ties that can confer stability, but those are on longer timescales and they're playing out on attractors that are different than the ones I'm looking at. Because the dynamics that I was looking at were the dynamics of the market system. And these dynamics, long timescale social dynamics, are illigible effectively to the market system. So my conclusions are applicable to the market. And those conclusions are that Attractor Reconstruction and property value time series did reveal a nonlinear deterministic system. The amount of dissipation measured was larger for the wealthy regions, and that market system dynamics are revealing inequitable responses to disaster events. And then my last little plug. The reference is in there. I hope you understand the technique. This is a technique I think that can be useful to just measure stability broadly. If you have a time series, this is a technique that you can use. Right now we have the MATLAB code available if you want to use that. We're going to try to work on getting a Julia version together. But yeah, use the tool. And thank you. Happy to entertain questions.
Any questions? Grad students first. Yes.
Yeah, so your lambda metric, I want to make sure I'm understanding. So you split up the phase space into two types of ways that you could define stability based on the basin size and based on the constituents. Is the lambda only measuring that convergent part?
Yeah. Okay. The basin part, I don't know anyone who knows how to measure that because it's a tricky one, right? You have to actually get out there to know. Like your system's already gone if you figured out that that's the edge of your basin of attraction. So yeah, there's less time. People spend a lot less time thinking about how to measure that one. Mine is to measure the convergence part. Yeah.
Okay. And then you had a nice visualization of that reconstruction of the Lorentz attractor. Can you do that sort of visualization of reconstructor for your time series, like with the spaghetti noodles?
Yeah, sometimes you can. It's funny. Till and I were just looking at a paper where someone actually showed their reconstructed attractor. You rarely see that because it's usually a mess. Yeah. The other reason you rarely see it is because I would have to take slices. Yeah, I'd have to flatten it in one of the dimensions, even if I did 4, let alone 5 and 6. And so it just becomes a mess. Usually it's just a messy thing. But sometimes you do see it.
And then my last question is, so you're arguing that you, like, given the same forcings for natural disaster, you're looking at just the internal components. In my head, those seem like they would be coupled. Like if I think about like a poor community, like especially in the case of this, like they would tend to be in flood-prone areas because the property value is lower, and like there's like the system already knows about those issues, and so you might end up with more people in that community that are in the same place.
That may be true, I think, in some examples, but I think on the scale that I looked at, I don't think that's necessarily true. And I know that from my experience in Florence, that county and that county right there, and there's, the impact of that disaster was kind of the same for all these counties, really. But quite a big variation in incomes in some of those different counties. But you're right, I will say that we haven't robustly gone in and looked. Like, is it the case that the actual forcing term in all of the sort of communities that were less stable, was the forcing actually worse? We didn't look at that, but I just think on this scale you wouldn't see that. But on a smaller scale, I think you're right.
Yeah, I guess if you're looking at the county level, that's different than looking at an individual, like whether or not you're within some reverse flood zone or not.
Right. Yeah. And not to mention, there's a lot of perverse places like where I live, where the closer you go to the edge, the richer it gets.
Yeah.
Yeah, great question.
Thank you for the talk. First, I had kind of like following up on like Evan's first question about like the basin. So thinking about like the energy sectors, I'm thinking like there's a lot of talk about like building a more sustainable grid where you have multiple sources of energy production and different types and how to optimize that system. So am I correct in understanding that sustainability in that sense is related to like changing the shape of the basin rather than changing the convergence and this type of metric?
Well, I'm not.
May not be.
That's a pretty deep question, and I don't know that I have a good answer if I can relate it to those energy considerations that you brought up, which are really interesting. But I will say that the shape of the basin and the flow convergence are the same thing. But you can think of it like a bowl. You know, the shape of the basin, if the bowl is really steep, the flow convergence is really strong in the bowl. And so, yeah, those are one of the same. The basin thing that I was pointing out more was like, where's the rim of the bowl? Like, where is it that if you push, it actually comes out of the bowl and goes somewhere else? Yeah. But my metric and most of these other metrics are trying to attempt to measure, in essence, what the shape of that bowl is like, the flow convergence. But a really good question about the energy. That's a good question. Yeah.
This is really cool, and I appreciate that you have code. That sounds like there's lots of time series that'd be fun to play this with.
Yes.
The one area that I'm familiar with critical slowing down where it's been applied a lot has been kind of on ecosystem tipping point stability, particularly with things like
Ponds,
ponds and lake ecosystems where there is, you can see something like that, right? You see a system in one state, say in a species abundance or something, and then you see a system that suddenly becomes very less resilient and lots of big changes and swings and then a new state. And so what would your model show for that? Or like, do you...
I think if it was a simple system like a critical slowing down, bifurcated fixed point, my system would work on that one as well. Right, because like all I'm measuring is convergence, and in that one, so the thing about mine, I guess, is that mine is useful whether your convergence is happening outside of the attractor or even in the attractor. Right, like if you do del.f for the Lorentz system, it's converging everywhere in space. So if you're inside the attractor of mine, it'll still measure the convergence. And what's useful about that is that dissipation is not only getting your return to an attractor faster, which mine will certainly measure like critical slowing down does, but mine also is capturing, if you're just in the attractor and you measure a lot of dissipation, you'll know that if you get kicked, you won't go so far from the attractor either. But the short answer to your question is, mine would give the same answer as critical slowing down on those systems. I think if you were going to have to decide maybe which one was more useful, you might take a model to kind of, what the model's saying is this much stability, critical slowing down saying this, yours is saying this, like which is jiving with the model better maybe? It's a good question.
So your description at the end with the property values and so forth, it reminds me, it just cried out, climate justice.
Yeah, absolutely.
So could you see this being used in a more widespread way to essentially quantify climate justice? And then with your bar graph example, how is your methodology superior in extracting information compared with more conventional statistics if you just classify groups by roughly and poor and
yeah, so yeah, good question. I guess I'll tackle the second part first. So I didn't mention this, like similar with the stock market, if you just look at, you split the two time series up in these groups, and you kind of start looking for some basic things like, is the variance difference in each, or leptokurtotic more in one or the other, or something like this, you don't see anything. I didn't do an exhaustive search through a bunch of different statistical measures. Maybe there is one out there that might indicate something interesting. So that's a great thought.
I was thinking more just conventional, so it sounds like you covered the conventional.
Yeah, the conventional stuff we looked at, yeah. And then your other question about climate justice, yeah, I hope so. Like I haven't published this yet, this application. It's on my to-do list for the summer. And I hope that it gets into that world and gets those eyes, because I think that there's, like I said to Motivator, there's so much time that gets spent on, well, the forcing's worse over here, and that's why they're going to suffer more. I think it's really important to look at some of the processes that we can control, like that are conferring stability. Like when I'm thinking about Florence, something simple like we had a hurricane a year after Florence, and I was driving to the beach the next morning. Electric was out everywhere. First neighborhood that got electric on, the wealthiest neighborhood in my whole community. So little things like that, this is pointing a finger at, and that's stuff that's fixable on a short time scale, as opposed to stopping sea level rise for the Maldivian people. That's a tougher one to stop on a short time scale. So I hope this gets into those eyes and promotes those kind of thinking, like what kind of processes can we add to these systems that provide dissipation and confer stability?
So how would you distinguish forcing in the case of, say, a heat wave and urban heat islands, which are known to be different depending on where you live in the city. And oftentimes it is the poorer areas of the city that get more heat. So in a sense, the large-scale meteorological forcing is the same, but yet the small-scale forcing is not. But yet that stems probably from this injustice issue in the first place.
Yeah. That is a tough one, and I mean I'd have to analyze that one specifically and try to get some answers for it. But that's why in this first application it's more just a glom of all kinds of disasters on a huge scale, and you just glom it all together and hope that some of those nuances are smeared out in the wash. But if you zeroed in on some of those impacts, that would be interesting to do for sure. Yeah.
Well, it's encouraging because we tend to talk qualitatively about these justice issues, but it's nice to see some way, to quantify it, to really sink your teeth into it,
right.
show it.
Right. Yeah, thanks.
Okay. Well, let's thank our speaker once more. Wow, very cool.
Thank you. And I'll just announce we have one more CPEP seminar for this semester next week on May 3rd. That's going to be our very own Stephanie Henderson, who's faculty here in Atmospheric Sciences. She's going to talk about the extratropical impacts of the Madden-Julian oscillation. So start thinking about tropical, extratropical connections in the climate system. And with that, we'll conclude our CPEP seminar series.